Now that we know how to get equations for tangent planes, we're going to use them to come up with linear approximations, and we're going to see how we can involve differentials and change in this process. If I want to approximate a surface function in a region near a given point, the equation of the plane gives me a place to start with that approximation, because remember, I'm very, very close, so that the region near that point looks like a plane, and a plane that lies tangent to it is going to do a good job of approximating the surface at that point. So I'm going to use these equations of tangent planes to compute a linear approximation of the function. And essentially, my linear approximation as a function of x and y will be given by fx at ab times the quantity x minus a, plus fy at ab times the quantity y minus b, plus f at ab. So let's work an example. I want to find a linear approximation for the surface given by z is equal to 12 minus 4x squared minus 8y squared at the point -1 and 4. And I want to use this approximation to then estimate the function value of f at the coordinates -1.05 and 3.95. So my linear approximation, L of xy, will be given by the partial derivative of f with respect to x evaluated at ab times the quantity x minus a, plus the partial of f with respect to y at ab times the quantity y minus b, plus my function f evaluated at ab. ab is -1, 4. fx at -1, 4 is given by -8 times -1, which is 8. fy at -1, 4 is -16 times 4, which is -64. My linear approximation, L of xy, becomes 8 times the quantity x plus 1 minus 64 times the quantity y minus 4 minus 120. This simplifies to L of xy is equal to 8x minus 64y plus 144. Now I'm going to use this approximation to approximate f at the points -1.05 and 3.95. This is equal to 8 times -1.05 minus 64 times 3.95 plus 144. This gives me an approximate value for my function of -117.2. Now let's talk about differentials here. Remember that an exact change in y, delta y, is the exact change in my dependent variable as x goes from x to x plus dx. And this can be approximated by what we call the differential, dy. dy is equal to f prime of x times dx. This approximation improves as dx approaches 0. So now, if I use the linear approximation for my function in the form z is equal to f of xy, we get f of xy is approximately equal to L of xy, which is equal to the equation of the plane tangent to the surface at the point AB, given by fx at AB times the quantity x minus a, plus fy at AB times the quantity y minus b, plus f of AB. The exact change in the function as we move from the point AB to the point xy is given by delta z is equal to f of xy minus f of AB, so that delta z is approximately equal to the linear approximation L of xy minus f of AB, so that delta z is equal to fx at AB times the quantity x minus a plus fy at AB times the quantity y minus b. The quantity x minus a is dx, and the quantity y minus b is dy. So if I let f be differentiable at the point AB, then the change in z is equal to f of xy as the independent variables change from the point AB to the point a plus dx and b plus dy is denoted as delta z, and it can be approximated by the differential dz, where delta z is approximately dz, which is equal to fx at AB dx plus fy at AB dy. Let's work an example. I want to use differentials this time to approximate the change in z is equal to negative x squared plus 3y squared plus 2 when the function changes from the point 1, 4 to the point 1.1, 3.9. So my equation that I'm looking for is dz, which is equal to fx at AB dx plus fy at AB dy. dz is equal to fx at 1, 4 dx plus fy at 1, 4 dy. fx is negative 2x. fx at 1, 4 is negative 2. fy is 6y, and fy at the point 1, 4 is 24. My dx is 0.1 and dy is negative 0.1. So that dz is equal to negative 2 times 0.1 plus 24 times negative 0.1. This gives me negative 2.6 as the approximation for the change in z as x goes from the point 1, 4 to the point 1.1 and 3.9. Here's another example. I have a volume of a right circular cone with a radius r and height h, which is given by v is equal to pi r squared h divided by 3. I want to approximate the change in the volume of the cone when the radius changes from r is equal to 5.4 to r is equal to 5.37, and the height changes from h is equal to 12.0 to h is equal to 11.96. My dv, the change in volume, is equal to pi over 3 times the quantity 2rh dr plus r squared dh. My dr is negative 0.03 and my dh is negative 0.04. So that dv is equal to pi over 3 times the quantity 2 times 5.4 times 12.0 times negative 0.3 plus 5.4 squared times negative 0.04. This is approximately equal to negative 5.293. Now you get to try it. Again, I have the volume of a right circular cone with radius r and height h, and this volume is given by v is equal to pi r squared h divided by 3. Pause the video and approximate the change in volume of the cone when the radius changes from r is equal to 6.3 to r is equal to 6.6, and the height changes from h is equal to 3.5 to h is equal to 3.48. When you're ready, restart the video to check your understanding. So I know that r is changing from 6.3 to 6.33, which gives me a change in r of 0.03. And I know that h changes from 3.50 to 3.48, which gives me a change in h that is equal to negative 0.02. dv is equal to pi over 3 times the quantity 2rh dr plus r squared dh. Again, dr is 0.03 and dh is negative 0.02. dv will therefore be given by pi over 3 times the quantity 2 times 6.3 times 3.5 times 0.03 plus 6.3 squared times negative 0.02. This is approximately a change of 0.554. Let me know if you have any questions about finding approximations when I'm using the equation for a plane tangent to the surface.